Welcome back, everybody. I'm here on page 6 of the Chapter 10 lecture note outline packet. And the last time we went through the different individual gas laws. So we looked at the effect of pressure and temperature and volume, all of these things in an individual way. Now, today what we're going to do is take all of those simplified sort of one-off gas laws and we're going to combine them. We're going to see how they're combined into a master gas law that we'll call the ideal gas law. And then after we learn about the ideal gas law and how it works, we're going to solve a few simple gas law problems. So with that, let's go ahead and get started. So with the individual gas laws, we saw Charles' law indicated that volume and temperature are directly proportional to one another. Pressure is also directly proportional to temperature, and we found also that volume is directly proportional to N, or the number of moles of a gas. This is Charles' law, Lusac's law, and Avogadro's law. Now, because both volume and pressure are directly proportional to temperature, we can rewrite this by combining these two statements into one. Specifically, we can say that because volume is directly proportional to temperature, and so is pressure, that the volume times the pressure should also be directly proportional to temperature. We can also combine Avogadro's law into this expression as well. Notice that the number of moles is directly proportional to the volume. So if we had the temperature times the number of moles, that would still be directly proportional to the volume. So we can put N, the number of moles, over on this side. So what we have now is a proportionality that expresses the relationship between volume, pressure, temperature, and moles. Converting this proportionality expression into an equation requires some constant that we'll call K. K allows us to correlate the pressure, volume, temperature, and moles. So if we rewrote this including K, we would have the expression PV equals KNT, where K is some constant. Now, the equation in this form would be quite valuable to somebody who needed to know specific parameters about a gas. So for example, if they knew how many moles there were in the temperature, they could also predict things like the volume or the pressure. Now, the only other missing piece they would require, besides, of course, the conditions, would be that constant K. So, of course, people are very interested in determining what is that K? Is it constant for a gas? Does it change depending on what situation the gas is in? What's going on with K? So to determine K, of course, you have to isolate K on one side of this equation. And if we do that, we see PV divided by NT is equal to K. So determining K is just a matter of measuring the pressure, the volume, and knowing the number of moles and the temperature for a given gas. And it turns out, possibly surprising, that K happens to be exactly the same for every gas. So if you go out and you do this with different gases, you get the pressure, the volume, the moles, and the temperature, you'll find K is always the same. Now, it turns out because this K is always constant, this turns out to be fairly important, especially for gases. And because it's so important, we actually assign it its own character or its own symbol. We assign it the character R, which is also known as the ideal gas constant. We say ideal because we're referring to an ideal gas, and it turns out in the real world, actual gases do have some small variations that can be accounted for through various effects. So what is the value of R? Well, it turns out R can be represented with a number of different values depending on the units that are used. The one we will use is R is equal to 0.0821, and then a series of units that I want to show you now. Notice that R, which is represented over here as K, R is equal to P times V divided by N times T. And each of those parameters has its own unit. So the units for R will be 4. We'll have 4 different units, one for pressure, one for volume, one for moles, and one for temperature. So let's talk about what each of those units is for this value, 0.0821. For pressure, we're using the volume unit atmospheres. For volume, we're using the unit liters. For moles, we're just going to stick with moles, MOL. And then for temperature, we will use the Kelvin. This is the unit system that we use to get this value 0.0821. And we usually write the units like this: liters times atmospheres. That's on the top because we have pressure times volume. And then we're dividing that by the moles times the temperature. So it's moles times temperature, which is Kelvin. So mole times Kelvin. So this is the ideal gas constant R. R is equal to 0.0821 liters times atmospheres divided by moles times Kelvin. We can put this into our equation and it would look like this. PV is equal to N times that constant R times T. This is known as the ideal gas law. And I often like to rewrite it as follows. PV divided by NT is equal to R. Now, the ideal gas law is really useful in this form because we've isolated the constant from the variables. And that means if we change the variables, we should always end up with the same constant. So that's useful because we might have some initial conditions where the pressure, the volume, the moles, and the temperature is known, and then some of those variables change. Even if they change, they still have to be equal to R. Let me show you what I mean symbolically. If we had initial pressure and initial volume, initial moles and initial temperature, and we divide those two, we would end up with R. But similarly, if we had a different pressure and a different volume, different number of moles and a different temperature, it still has to equal that same constant. That's because R is always a constant. So we might have initial conditions over here on the left that are equal to R, and then final conditions over here on the right that are also equal to R. And this is very useful because we can solve a lot of gas problems in a very simple way by using this setup. So we're going to see that on the next page. Let's go take a look. So let's get into actually using some of these equations and laws to solve some simple types of gas law problems. We're going to see two types of gas law problems. The first type we'll look at are problems that involve a change in the conditions. So we have conditions at time one and then later conditions where something has changed. By conditions, I mean things like the temperature or the volume or the pressure or the number of moles. That's one type of problem we'll see, changing conditions. Another type of problem we'll see are just problems that want us to figure out something about the gas, but there are no conditions that are being changed. Now, for both types of problems, you always want to do the same thing when you look at a gas law problem. Always start out by listing out the conditions that are given. Even if the conditions aren't changing, always write out these conditions. And by conditions, again, I mean pressure, volume, moles, and temperature. And I'll show you an example of how I like to do it down below. So let's start off by looking at problems that involve a change in the conditions. The method that we use to solve these problems relies upon, again, that fact we looked at before, that P times V divided by N times T is always constant. It's always equal to that ideal gas constant R. So this is very useful for problems that involve changing conditions because it allows us to relate the conditions initially to the conditions at the end. So let's see how that works in this first example below. Now, as we read through this problem, let's try to figure out what are the conditions that are provided, and are they conditions initially or conditions at the end? And then we're going to write down what each of them is. So it says a gas has a volume of 6.85 liters at a pressure of 0.650 atmospheres. What is the volume of the gas if the pressure is decreased to 0.435 atmospheres? Okay, so we're given initially 6.85 liters and a pressure of 0.650 atmospheres. Let's write those down. So we're given a volume and we are given a pressure. And these are initial volumes and initial pressure because they happen before the change. So the initial volume, or V1, is 6.85 liters. And the initial pressure, or P1, is 0.650 atmospheres. So those are our initial conditions. What are the final conditions? Well, it says, what is the volume of the gas if the pressure is decreased to 0.435 atmospheres? So we're being asked, what is the new volume of the gas? That would be V2. And the new pressure, or P2, is 0.435 atmospheres. Those are our final conditions. Now, what about the moles and the temperature? Notice that neither one of these two values is mentioned here. Moles or temp are not mentioned. That means they are not changing. So we are not increasing or decreasing the number of moles, and we're not also changing the temperature. So that's important. It helps us get to a quick solution for V2. Remember that P1 times V1 divided by N1 times T1 is equal to R, and so is P2 times V2 divided by N2 times T2. Now, if moles and temperature are remaining constant, we can cross out moles and temperature on both sides of this equation. That leaves us with the simplified equation, P1 times V1 is equal to P2 times V2. Notice that this is the same as Boyle's law. So in fact, we actually just derived Boyle's law from the ideal gas law. Now, how do we actually go about solving this? Well, that's right, we need to actually solve this equation for V2. So let's isolate V2, plug in the values of V1, P1, and P2, and then we will have our new volume. So V2 is going to be equal to P1 times V1 divided by P2. Now we just have to plug in these values. P1 is 0.650, that's units of atmospheres. We're multiplying that by the initial volume, which is 6.85 liters. And then we're dividing this by the second pressure, which is 0.435 atmospheres. Now notice we have atmospheres at the numerator and in the denominator. We can cancel both of these units out. That will leave us with the units of liters. And with 3 significant figures, the calculated value is 10.2 liters. Now, it's always a good idea after you've done a gas law problem to verify that your result makes logical sense. So what we're seeing here is a change in the pressure, and the pressure is decreasing. Now, what would we expect to happen to the volume if the pressure is decreased? Well, that's right, we would expect the volume to increase. Now, it's a good idea to check that it did. We see 10.2 liters. That is definitely an increase over the initial volume, which was 6.85 liters. So yes, this result makes sense. Okay, so now that we see how we can use the ideal gas law to help us solve gas problems that have changing conditions, let's try another example. Now, what I want you to do is pause the video and see if you can do this yourself. Now, one thing to remember whenever you're doing gas law problems like this, make sure that your units that you're using for things like pressure, temperature, and volume match the units for the value of R that you have. And our value of R uses liters, atmospheres, moles, and Kelvin. So always make sure your units are converted into those units before you actually plug in the values and solve for the missing variable. All right, let's take a look at how this problem is solved. So in this example, we see a change in temperature. The temperature is changed from 455 Kelvin to a temperature given in degrees Celsius. Now that degrees Celsius, we're going to need to convert into Kelvin before we can solve this problem. We're being asked what is the new volume, and we're given the initial volume. So first, let's just write out all of these different temperatures and volumes initially and at the end. So I've written out my temperatures and my volume. Now notice I put a little decimal place next to the 50. I wanted that to be 2 significant figures. That's why I placed that decimal point there. It should have been in the problem, but I must have left it off. Now the next thing we need to do is convert that degrees Celsius into Kelvin. So how do we do that? Well, to convert degrees Celsius into Kelvin, we need to add 273.15. Notice that my temperature reading, 50 degrees Celsius, is only significant out to the ones position. That means the result of my calculation here ends at the ones position as well. So the 3 there is the last significant digit. Now I'm not going to round until the very end after I've done all of my calculations. All right, so now what's the next step? Well, what we should recognize is we have things that are changing and things that are staying the same. Notice the temperature and the volume are changing, but nothing is happening to the pressure and the number of moles. So pressure and moles are constant. So when we write out our expression between pressure, volume, moles, and temperature, we can cross out the pressure and the moles on the left and the right. This leaves us with the simplified V1 over T1 is equal to V2 over T2. This is also Charles' law, so we've derived Charles' law from the ideal gas law. Now all that's left for us to do is to solve for V2. We can multiply both sides by T2 to isolate V2. This gives us V2 is equal to T1 times T2 divided by T1. So when we plug in our V1 and our T2, and we're multiplying those by each other, and then we're dividing by T1, we see that the temperature units, Kelvin, will cancel, and we're left with units of liters for volume. And we have 3 significant figures at the top is our smallest one, and then 3 at the bottom also. So our answer should also have 3 significant figures, and we get 2.60 times 10 to the fourth power of liters. So does that make sense? Well, we have a smaller volume, right? The volume decreased from 3.66 times 10 to the fourth liters to 2.60 times 10 to the fourth liters. So we saw a decrease in the volume. This was accompanied by a decrease in the temperature. So yes, this is the expected result. All right, so let's go to the next page and look at some more examples. So as I mentioned earlier, we also see problems that involve unchanging conditions for a gas. So this is usually just try to figure out what the number of moles are, or what is the volume, or what is the current pressure, or the temperature. By knowing three of the variables, we can find the fourth. So with this kind of problem, all we're going to do is to first write out all of the variables that we have, all of the parameters, and then we're going to make sure we convert them into the right units. So we're going to convert pressure into atmospheres, volume into liters, temperature into Kelvin, and we'll keep moles as moles. And then we plug all of this into the ideal gas law and solve for the missing variable. So let's take a look at this example. It says a sample of hydrogen gas is collected in a bottle over water. The volume of the sample is 185 milliliters at a temperature of 25 degrees Celsius. The pressure in the bottle is 736 torr. What is the mass of the hydrogen gas in the bottle? So before we start worrying too much about how we're going to get a mass out of this thing, let's just first write down what we're given. We're given the pressure, that's 736 torr. We're given the volume, that's 185 milliliters. We're not given the number of moles, so let's write a question mark there. And then we're given the temperature is 25 degrees Celsius. Let's start by converting the temperature into units of Kelvin. To do that, we have to add 273.15. If we do that, we get 298.15 Kelvin. You can see I've underlined the significant digits in that calculated result. The next thing we need to do is convert torr into atmospheres. So for that, let's write out a conversion factor. We've got 736 torr, and we're going to multiply that by the conversion factor that goes between atmospheres and torr. Remember that 1 millimeter of mercury is equal to 1 torr, and 760 torr is equal to 1 atmosphere. So our conversion factor looks like this, and we get 0.968 atmospheres from 736 torr. That is 3 significant figures. Let's also convert our volume, which is in milliliters, into liters. Remember that there are 1,000 milliliters in 1 liter. So our conversion factor would look like this. We have 185 times the conversion factor with 1 liter on top and 1,000 milliliters on the bottom, and we get 0.185 liters. Now let's talk for a minute about how we're actually going to solve the problem where we're being asked what is the mass of the hydrogen gas in this bottle. Well, recall that if we know the number of moles of a substance that is present, we can convert that into the mass, right, into grams, by using the molar mass conversion factor. We just need to have the number of moles, which is N, and notice here that N is missing. So once we solve for N and figure that out, we can convert it into the mass using the molar mass. Well, how do we find N? Well, to find N, we can just rearrange the ideal gas law. Recall the ideal gas law is just PV equals nRT, and we need to solve this for N. So if we want to isolate N, we need to take PV and divide it by RT. This will leave N, or the number of moles. Now we just need to plug in our pressure, volume, R, and the temperature, and we'll have the moles. We can convert that into mass. So let's write all this down. N is equal to the pressure, which is 0.968 atmospheres, times the volume, which is 0.185 liters, and then we need to divide that by RT. Well, remember R, the ideal gas constant, is 0.0821 with the units liters times atmospheres divided by moles times Kelvin. We're going to multiply that by the temperature in Kelvin, which is 298.15 Kelvin. We do all this, we can type this into our calculator and get 0.00732, and that's moles of hydrogen gas. Now all that's left for us to do is to convert this moles of hydrogen gas into the mass of hydrogen gas using the molar mass. So once we do that, we get 0.0732 moles times 1 divided by 2.016 grams. I got that by adding up the atomic mass units for hydrogen, and we're left with 0.0148 grams of hydrogen in the bottle. So now we know how to solve these simple types of gas law problems where we have changing conditions and unchanging conditions by using the ideal gas law or the derived individual gas laws that we can get from the ideal gas law. So with that, I'm going to end today's lecture. What you should do next is work on the problems that I have, the example problems I have in the lecture note packet on the next page. Work on those, and we'll start there next time. I'll show you the solutions to those problems, and then we will finish up Chapter 10 with some information about the kinetic molecular theory. I hope you're doing well. Let me know if you have any questions, and take care.